This is lecture 17 of CS47 Computer Organization Study. In this lecture, we'll look at two digital component, very important digital component that is frequently used inside microprocessor design. There are many more, so we'll pick up those other important part in CS147, but for this course, we need to understand at least two of them at this point. One of them is called a decoder. Okay, decoder as a circuit, it converts n-bit binary code into m-bit unique output. So it can be a multi-input, multi-output, but this n and m has a relation. So relation is n has to be less than equals to m, and m cannot be more than 2 to the power n. So that's what it is, like n less than equals m less than equals 2 to the power n. Now we often use this n to m line decoder, which produces m-bit code such that only one bit is at logic 1 at one time. Okay, so one is decoder, another is line decoder. Okay, decoder is like any circuit with a n input and m output, which satisfies this relation n less than equals m less than equals 2 to the power n. But the line decoder is a special type of decoder which converts n input to a m output, and only one such output can be 1 at a time. It means like all other output for a given input combination is 0 except for one of the output, which is at 1. This can produce like 2 to the power n or fewer minterms for a given n input variable. Okay, so usually, however, like it says a fewer minterms, but when we often talks about a line decoder, n to m line decoder, like 2 to 8, no, not 2 to 8 cannot be possible, 2 to 4, 3 to 8, and that kind of thing, we kind of stick to this 2 to the power n relation. Like if the n is 2, output is 2 to the power 2, or number of output is 2 to the power 2. If n is 4, number of output is like 2 to the power 4, which is 16 output. And in that output, with each combination of this input bit pattern, only one of the output turns to 1 and everything else stays to 0. So that's an n to m line decoder. We can think of 1 to 2 line decoder in a very simple circuit. Input A, okay, and that input is basically reflected at an output directly as m1 output, and m0 output is an inversion of input A. So this line decoder output is usually marked as a minterm representation, m0, m1. Actually, they are minterm, right? If it is a one variable, then it has a two minterm, like 1 and 0. So minterm 0 and minterm 1, let's say, that means if A is 0, it is minterm 0, right? So that way minterm 0 line goes 1 and minterm 1 line stays as 0. Whereas if A is 1, that means it's a minterm 1 in terms of minterm definition. So your M0 output stays as 0, but M1 turns to 1. Similarly, we can have like 2 to 4 line decoder combining 2 1 to 2 line decoders, and this is also the truth table like this, like it has a 2 input A1 A0, where A1 is assumably it's a MSB side and A0 is the LSB side of the value of the binary pattern. So this guy has 4 output, M0, M1, M2, M3. For each combination of A0, A1 and A0, there can be like maximum 4 combination. It will corresponding minterm output will turn to 1. So if it is 0 0, that means it's a min term 0. That means min m0 will be 1, everything else will stay 0. 0 1, similarly m1 will be 1, every other output becomes 0. 1 0 is basically m2, min term 2, that corresponding to that output, min term 2 level. That output becomes 1, everything else is 0, and 1 1, m3 would be 1 and everything else is 0. So it's kind of, this circuit shows that like what min term came as an input, right? So it indicates which min term came as an input. So this is the functionality of any line decoder, and very useful in the digital circuit design, especially for the complex designs. So this specific component we can start from the basic one, like 1 to 2 line decoder, and then start combining them through the AND gate. So you all know that M0 is, min term 0 is defined as A1 bar, A0 bar. So what we take A0 bar from the 1 to 2 line decoder and A1 bar from the 1 to 2 line decoder, and combine those logic through an AND gate, and that become my M0. Similarly, M1 we combine A1 bar and A0, M2 we combine A1 and A0 bar, and M3 we combine A1 A0. So this becomes your 2 to 4 line decoder circuit. So before I go into this page, let me stick to the previous one. So you can actually now use that 2 to 4 line decoder and another 1 to 2 line decoder and combine their individual output through another set of gates, logic gates, as to make 3 to 8 line decoder. Okay. And then from the 3 to 8 line decoder, you can combine another 1 to 2 line decoder and use bunch of AND gates to make a 4 to 16 line decoder. That's one way, one choice. And another choice would be like use 2 to 4 line decoder and basically deploy another set of AND gate at the output side. Will be you can make a 4 by 16 line decoder. Now, if you think that if you want to count the number of AND gates needed at the output stage of a line decoder, 1 by 2 doesn't have any AND gate. Now 2 by 4 will have the last stage will have that 4 AND gates, right? Then similarly 3 by 8 will have 8 AND gates at the output side, the last stage of that circuit, which basically produce M0 to M7 in that circuit, 3 to 8 bit circuit. And similarly, you can just think like if it is in 4 to 16, then last stage will have 16 NAND and so on and so forth. So if you are given a problem that, hey, give me number of AND gates in a like say 5 by 32 line decoder, 5 to 32 line decoder, you can definitely count at least the last stage. You can count that is an output of 32 AND gates, and probably you combined maybe 4 to 16 line decoder with 1 to 2 line decoder. Then that inside that 4 to 16 line decoder you have a 16 AND gate, and inside that 4 to 16 line decoder you might have like 3 to 8 line decoder. So it will have an 8 AND gate and so on and so forth. So that's one kind of problem you can face. You can imagine like arbitrary given number of N to M line decoder. How many number of gates are there, or how many number of, let's say, basic gate. Like AND is not a basic gate, AND is combined of NAND and inverter. So this kind of problem maybe you want to practice a little bit to make your conception clear about the circuit and how we can expand from 1 to 2 to 2 to 4 to 3 to 8 to 4 to 16 and so on and so forth. That will help you to conceptualize this whole circuit. Now, we construct from here, from the previous page, one special circuit with an enable mechanism. What is an enable mechanism? So we see that in the previous page, that given an input combination, one of the output is stage 1. There is nothing like we cannot turn off this circuit in a very loose sense. I'm saying the turn off means what it really means. I cannot achieve an all zero combination, but sometimes it is in the digital circuit, it is needed to kind of turn off the line decoder, okay, and make it all zero if I don't want that decoder to decode anything, okay. So what we do in that case, we deploy another set of AND gate, okay. So if you see the outer but one, this dotted big block, big partition, I would say, that represents the decoder from the previous page, okay, this previous page. Then each of the output of that decoder is run through another set of AND gate and logic with the other terminal connected to a signal called E, okay. So now what happens, E stands for enable. What happens if E is 0, since 0 is the controlling value of the AND gate. So for AND gate, if any one of the terminal logic is 0, output is 0, no matter what the other terminal value is. So that means if E is 0, now we are concentrating on this truth table, E is 0, then it doesn't matter what value A1 and A0 is. It's a don't care. I don't care those values. Doesn't matter. All the output will stay at 0. M0 0, M1 0, M1, M2 0, and M3 0. Only if you set this E to 1, this whole component now start acting as a 2x4 line decoder circuit. So this is what a 2x4 line decoder with enable. So we can really control when this circuit start, when it decodes something or it does not decode something. So we have kind of turn on and off in a logical sense, a switch to turn on and off its functionality. Right? So if it is turned off, all the output remains 0. Only once it is turned on by setting this E terminal to logic 1, this whole circuit start acting as a 2x4 line decoder as described in the previous slide, as this one.